Thank you. A pleasure to be here this evening to tell you about the end of everything. As you can see from the subtitle, I'm going to be talking about the fate of the Earth, the fate of the Sun, the fate of the galaxy, and ultimately the fate of the universe. So if you'll forgive me paraphrasing Buzz, we're going to go to eternity and beyond. So I'll be giving a little bit of a prologue, but then I'll be talking about the future of the Earth, the Sun, and the solar system, not necessarily in this order, but then talking about the far future of what's happening to stars and galaxies, and then we'll be looking at the far, 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 far future and the ultimate fate of the universe, which will leave you all thoroughly depressed, in which case I will finish with an epilogue on a slightly more upbeat note, hopefully, as this is close to Christmas. So I'm not going to be talking about the beginning of everything. That's a completely different talk, in which I described how the universe came to be some 13.8 billion years ago. It started life as a very small thing, the observable universe. Everything that we currently see in the observable universe was much, 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 much closer together, separated by centimeters rather than separated by hundreds of billions of light years. But this talk is about not how it all began, but where we're going from here. And to try and keep everything on track, either for this talk, or if you wish, if you want to take away a handout, a printed handout of the slides, in order to keep track of where we are, there's a timeline running along the top. And a red rectangle will move along there. Each square here represents 10 times further into the future. So we'll be looking at 1,000 years into the future, 10,000, 100,000, a million years, you know your powers of 10. We'll be going to 10 to the 9, a billion years into the future, and we'll be going to 10 to the 12, a trillion years into the future. And we'll be going a little bit beyond that when we get to that end of the scale. So I'm indebted to the work of Adams and Laughlin, who wrote a paper some 25 or so years ago, in which they laid out the astrophysical timeline of when things are likely to happen in the future. And I've used that paper to try and get my slides in the right order. So I'm not talking necessarily about the Earth, then about the Sun, then about the galaxy. I'm jumping around between different things, trying to put everything in the right order so the red rectangle simply moves along the screen. So let's assume that we don't kill ourselves in a nuclear war. Let's assume that we get climate change under control. I'm not talking about the next 10 or 100 years. Let's jump a little bit. 10 to the 4 years into the future, various things are going to change. For instance, the Earth's axis precesses. The direction of the Earth's axis at the moment points to the star, or close to the star Polaris, but it precesses on a timescale of 26,000 years. And it actually traces out a large circle on the sky. So at the moment, the Earth's axis points towards the star Polaris. Polaris just happens to be a reasonably bright star close to where the pole is currently pointing. But in roughly half of 26,000 years, the axis of the Earth is going to point in a different direction. And it's going to be very close to the very bright star, Vega, which is significantly brighter than the pole star that we see at present. That's going to make it very easy for Boy Scouts to point out which way is north compared to now. But there are other consequences to the Earth's axis changing. At the moment, the Earth's axis is such that we are pointing towards Polaris, which means we have a northern winter, in other words, the axis pointing away from the sun, when we are closest to the sun, perihelion. Whereas when the axis points the other way in another 10,000 years or more, it means that northern summer is going to occur when we are closest to the sun. So that's going to exacerbate the seasons. There are a number of reasons why the seasons change, depending on the Earth's axis and depending on the Earth's orbit. Any variation in the Earth's climate due to either the Earth's spin or the Earth's orbit are collectively known as Milankovitch cycles, and we'll hear that again in due course. Let's go 10 to the 5 years into the future. Some of you may remember, perhaps the younger members of the audience don't, the Voyager space probes were launched back in the 1970s. They went past Jupiter and Saturn for Voyager 1. Voyager 2 went past Jupiter, Saturn, and then went on to Uranus and Neptune. But both of these, because of the gravity assists they obtained, especially from Jupiter, are now going fast enough that they will be leaving the solar system. And on this timescale of order many tens of thousands of years, these two space probes are going to leave the solar system. At the top there, Voyager 1 is heading out of the solar system towards the star system known as Gliese 445. And at the bottom here, Voyager 2 is heading out of the solar system in a different direction towards the star system Ross 248. Pioneers 10 and 11, also on this diagram, they are not traveling quite as fast. They were launched a few years earlier. Pioneer 10 is heading off into the direction of Aldebaran, the bright star in the constellation of Taurus, and Pioneer 11 is heading off in the direction towards the center of the galaxy. We'll come back to those space probes later. We know that Earth has been through ice ages. Looking at the historical record, we know that Earth goes through ice ages roughly once every 100,000 years or so. And we know, again from the records, that the Earth entered a relatively warm period in between ice ages relatively recently. That means we are due for another ice age approximately 100,000 years from now. This is another consequence of changes to the Earth's orbit. This is another example of a manifestation of the so-called Milankovitch cycles. We know that the Earth's spin is actually slowing down. The moon tugs on the Earth, it raises tides on the Earth, and there's an angular momentum exchange between the Earth and the moon. As the Earth slows down and loses angular momentum, the moon is stealing that angular momentum and it's pushing the moon away from the Earth. This is something I talked about in a separate talk, in which the seconds, or at least leap seconds, have to be added to clocks to keep the rotation of the Earth synchronized with our clocks. If we want, just like the calendar, to be synchronized with the seasons, if we want the Earth's rotation to be synchronized with our clocks, we have to add leap seconds every once in a while. We haven't added a leap second for a few years, but generally speaking, the last second of the 31st of December, every once in a while, an extra second is added. But in 10 to the 5 years of time, the Earth will have slowed down so much that we'll need to add a leap second, not once in a while, not once every few years. We would need to add a leap second every day. In other words, the length of the day, now that the Earth has slowed down, is 24 hours and a second, approximately. We know that things are going to change beyond the solar system. We know that some stars are getting old and some stars are close to the end of their lives. For instance, this star is a very massive star called Eta Carinae. It's in the southern hemisphere, and it's a very unstable star because the nebula, the gas that we can see around this star, the star is in that very bright part right in the middle there, but this nebula we can see around the star has been the result of the outer part of this star being shrugged off. For thousands, if not tens of thousands of years, this star has been unstable and it's been unable to hang on to its outer envelope, and it's produced this nebula from the outer atmosphere of the sun being shrugged off. And this is a sign that this star is very unstable. We know it's quite massive. It looks like this is a candidate for a supernova. We don't know whether that supernova is going to happen shortly or in another 1,000 years. It is thought quite likely that this star will go supernova sometime in the next 10 to the 5 years, sometime in the next 100,000 years, but we can't predict exactly when. It might be beaten to the punch by Betelgeuse, the star that's in the constellation of Orion, which is easily visible from the northern hemisphere. Here, this is a genuine astro picture, but Betelgeuse has been artificially brightened by the person who took this image from Prague. That's Prague Observatory in the foreground there. That's an indication of what Betelgeuse might look when it decides to go supernova. It's not only going to be the brightest thing in the night sky, it'll probably be visible during the day for a while, because Betelgeuse is only 600 light years away, and that's fairly close for a star that's going to go supernova. But there are other stars that are perhaps supernova candidates. There's a certain type of star called a Wolf-Rayet star. When they die, they can produce so-called gamma-ray bursts, because not only do they release a lot of energy like a supernova, they are rapidly rotating systems. This particular one is 7,000 light years away, but because it's a rapidly rotating system, it can produce jets that fire off gamma rays when they decide to die. And the question is, are we in the firing line of one of these jets? If the Earth happened to be in the wrong direction, in other words, in the line of fire for this jet, it could, in principle, even though this object is thousands of light years away, much further, for instance, than Betelgeuse, which is going to go supernova, it is possible that a gamma ray burst from one of these stars could be a threat to life on Earth. Luckily, we do not seem to be in the direct line of fire, but there are lots of these objects around. These Wolf-Rayet stars are thought to be the precursors of supernova events. We're watching a lot of these stars to see what they do. Moving forward now, this is 1 million years into the future. There are certain spacecraft, for instance, Gaia is one of the spacecraft that is currently mapping out stars in our Milky Way. It's looking at the positions of stars extremely accurately and returning to map the positions of stars over and over again. The idea being you can see small star movements and you can get an idea of how the Milky Way is rotating. So we can only see a certain number of stars. We can't see all the stars in the Milky Way, but we can see quite a lot that are on, if you like, our side of the galaxy. And by mapping out what stars are doing, we realize that all stars are moving independently around the center of the Milky Way, and some of those neighbors of ours might come a little bit close and then drift away again as we independently orbit the center of the galaxy. And one star in particular, it's been predicted by Gaia, in 1 million years or so is going to get very close. Gliese 710 is going to get so close it will actually enter our solar system. So there's our sun surrounded by an Oort cloud. You can't see the planets, you can't see Mercury, Venus, Earth, Mars, Jupiter, etc., because they are all contained in that tiny dot in the middle. This is the Oort cloud, a huge cloud, maybe a light year or so across, that contains trillions of icy particles, all orbiting around the sun at the center. But when Gliese 710 comes close to us, it'll enter the Oort cloud and it will disturb the Oort cloud. All of these particles that are happily orbiting the sun will be disrupted, and it will probably produce a whole load of comets coming into the inner solar system and giving us a spectacular display. It's been estimated that there will be naked eye comets, probably many per month, for 1 million years when this star starts perturbing the Oort cloud. Interestingly, for a little while, our solar system will actually have 2 suns in it, just like other systems that I'm sure you recognize. Okay, it's not quite like that. They won't appear to be the same size in the sky, but we will have 2 suns in our sky for a while in about 1 million years' time. Still on a timescale of 10 to the 6 years into the future, why have I shown you a picture of meteor crater? One, so that we can notice what a stroke of luck that this impact just missed the visitor center. I mean, what's the chances of that, eh? The second thing is you think, well, does that mean we're expecting an impact like this every 1 million years? No. What it means is that on a timescale of 1 million years, we can expect any signs of an impact crater to be eroded by the erosion of the Earth. The wind and rain, the continuous erosion due to weathering is going to mean that any impacts that produce craters, anything more than 1 million years ago, we wouldn't really expect to see any signs of them. So this is relatively recent. This is only tens of thousands of years old. Anything 1 million years old of a similar size, we would probably not even notice it if it was on the ground. You might say that, okay, that's true. The Earth has an atmosphere, we have weather, and therefore impact craters won't last very long. But surely impact craters will last forever, for instance, on the moon. Doesn't everything last forever on the moon? Well, no, there's no weathering with no atmosphere, but for instance, the footprints of the Apollo astronauts are not going to last forever, simply because although you don't have weathering, the moon is being bombarded with lots of micrometeorites. On Earth, we don't worry about them because they're absorbed by the atmosphere, but on the moon, these micrometeorites hit the ground, and effectively the ground is being pulverized with lots of tiny particles continuously raining down, which means the footprints are going to disappear, and eventually even the lunar hardware, the Apollo lander, for instance, and the rovers, they are eventually going to disappear under micrometeorite bombardment. 10 to the 7 years into the future. We're now talking about 10 million years from now. The Pioneer 10 and 11 probes that I mentioned earlier are flying out of our solar system. It might take them tens of thousands of years to reach the next solar system, so on a timescale of 10 to the 7, they will probably have already passed through dozens, if not hundreds, of other solar systems. And in case there's anybody to greet these particular ambassadors, we've put a plaque on Pioneer 10 and Pioneer 11 so people can tell it came from Earth. The plaque is, I'm not going to go through all the detail, but the plaque has a map on the left-hand side here as a pulsar map so that people in years to come can figure out where the pulsars are and figure out where Earth must be. And we've shown that the spacecraft came from the third rock from the sun. So if they wanted to, they could figure out which solar system it came from and specifically which planet it came from. But on a timescale of 10 to the 7 years, although it will have been through hundreds, possibly hundreds of solar systems, this plaque won't last forever because this plaque is flying through the interstellar medium. The space between stars is not empty. We tend to think of space as being space, nothing, but no, the space in between stars is actually full of tiny dust debris particles. They might only be micron size, only a tiny fraction of a millimeter, but there are lots of particles out there, especially when you think that this thing is traveling at tens of thousands of miles an hour, and after millions of years, it will have impacted lots of these particles. And hence, this plaque will be pitted and eroded to the point where it is essentially unreadable. So if any alien civilization picks up Pioneer 10 or Pioneer 11 as it goes through other solar systems, as long as they pick it up within the next 10 million years or so, they should just about be able to read the plaque and figure out where it came from. But anything beyond 10 million years or so, it's going to be too pitted, too eroded for anybody who picks it up to figure out where it came from. So its history, in that sense, will be lost. 10 to the 8, 100 million years into the future, we can ask ourselves, for instance, in our solar system, what is going to happen to Saturn's rings? But perhaps before we answer that question, we ought to ask ourselves, where did Saturn's rings come from in the first place? It is widely believed that Saturn's rings resulted from the destruction of a moon, either a moon that didn't form properly, or perhaps a moon that was maybe hit by another moon or hit by a comet, was pulverized, and all the debris that was left ended up forming the ring system. This is Mimas, one of the moons of Saturn, and it's thought that you would need a moon about the same mass as Mimas in order to make the ring system. But when you look at a moon like this, you might think to yourself,
that's not a moon, it's a space station.
Because it does have a rather odd crater in it there. But simulations have been done to try and work out, if you take something the size of Mimas, disintegrate it, how long does it take until the debris starts to spread around the orbit? Does it simply go round as a cloud for ages, or does it spread into a ring system? And simulations have been carried out, the credit is on the side there, take a moon, pulverize it, and then run the simulation to see how long it takes the debris to spread. Look at the timeline in the bottom right-hand side. It doesn't take millions of years, it takes hours, it takes days, it takes weeks for a ring system to actually form once you start with a whole load of dust and debris. So over this timescale of 10 to the 8 million years or so, all of this debris is circulating, but because there are so many particles there, all interacting with each other, they are slowly spiraling into the surface of Saturn. So on timescales of many millions of years, we will end up with the ring system that we know and love today. But if we continue forward for more millions of years, on a timescale of perhaps 10 to the 7 to 10 to the 8 years, we can predict that all of Saturn's rings, all of the particles in Saturn's rings, will eventually spiral down and rain onto the surface of Saturn. So on this timescale, the ring system of Saturn will be lost. So for those of you who like looking at Saturn through a telescope, get in now, because on this timescale, it will no longer be visible. This ring system of Saturn is not a stable system, it is an ephemeral, transient system. Something to bear in mind when we're thinking about the solar system generally, because we can build ourselves a clockwork orrery and watch the planets going round the sun, or a tellurian, which is the same sort of thing, looking at how eclipses form between the Earth, the Moon and the Sun. When we have clockwork systems, whether they're motorized or whether they're wind up, it doesn't matter, a clockwork system makes us think of Newtonian's clockwork solar system. But on these timescales of order, 100 million years or so, we have to remind ourselves that the solar system is actually chaotic. Much like with the weather, we can sort of predict that tomorrow there's going to be rain or it's going to be windy, but we can't predict what's going to happen in a month's time. So the predictability of our weather depends on the timescale you're talking about. The same for the solar system. We can predict where Jupiter is going to be in 1,000 years' time, no problem whatsoever. We can predict where Jupiter is going to be in 10,000 years, but we can't predict where it's going to be on a timescale of 100 million years. We don't even know not only where the planets are going to be, we don't actually know how many planets we're going to have in 100 million years. It could be that Jupiter has decided to eject one of the smaller planets from the solar system. We think it's happened before. Planets have apparently shuffled and reordered themselves in our solar system billions of years ago, so perhaps that will happen again. So we just have to remind ourselves, although we can wind back the clock and figure out where was Jupiter, for instance, 2,000 years ago, was it the Star of Bethlehem? We can do that calculation, but we can't run the clock forward or backward by these sorts of times, because ultimately the solar system is chaotic on these timescales. Still on a timescale of 100 million years or so, we can think about the way the sun goes round the galaxy. It takes the sun approximately 10 to the 8 years, 100, or roughly 200 million years to go round the galaxy, to do one circuit. At the moment, we're sitting there. Let me just point it out. There's the blob. You are here. We are sitting, roughly speaking, between a couple of relatively dense spiral arms of the galaxy. So the spiral arms are regions where the stars are more densely scattered than where we are at the moment. On a timescale of 10 to the 8 years or so, we are going to move from a region which is relatively unpopulated to a spiral arm. So at the moment, we're sitting in between spiral arms, relatively low density, not that many stars within, let's say, 10 light years of us. We're going to move into an area which has got a lot more neighbors. In other words, there's going to be many more neighbors within, let's say, 10 light years or so. What are the consequences of having lots of stellar neighbors? Apart from the night sky looking a little more spectacular, because we'll have many more neighbors, so there'll be more apparent stars in the sky for us to enjoy. But there's at least two consequences of having a lot of neighbors. One we've already thought about. For instance, when Gliese 710 gets close to us, it can disturb the Oort cloud and send a lot of comets and chunks of rock our way. So when we've got lots of stellar neighbors, when we are in a spiral arm of the galaxy, again, if we've got lots of neighbors, it's much more likely that one of those stars is going to get close to us, just because we're all orbiting the Milky Way independently. It's much more likely that one of those stars is going to get close and send lots of rocks into the inner solar system by disturbing the Oort cloud. We know that's happened in the past. If we look back the last 500 million years, we notice that there have been lots of extinction level events. The number of species that were lost is effectively documented, and we find that there are lots of spikes, 6 spikes in the last 500 million years or so. And it's quite possible that this is related to the fact that we've got a lot more neighbors every once in a while when we move into a spiral arm, and that gives us a much higher probability of getting hit with a big rock. The last one here on the right-hand side, the KT, the boundary between the Cretaceous and the Tertiary period, that's the one that killed the dinosaurs. That's the one that let us come out from being small furry creatures who are nocturnal. That allowed us to come out in the daylight because we're no longer going to get eaten or stomped on, and so that allowed Homo sapiens to develop. But it looks like on these sorts of timescales, 10 to the 8 years or so, we can expect another bout of large numbers of rocks coming our way. So that, of course, is just an artist's impression. We don't know exactly when it's going to happen. We just know it's going to be more likely on this timescale. If you look at the left-hand side, It looks like this particular large chunk of rock is really bad news for Italy. But of course, if it's a large enough chunk of rock, it's going to be bad news for the entire Earth. It's not just going to be one country that gets obliterated. It will be a global catastrophe. Species will be exterminated during one of these extinction level events. What we don't know, of course, is whether we will be one of those species or not. We've got a little bit of time to figure it out and make sure that Bruce Willis is available to push the asteroid off course or to figure out other ways of avoiding disaster from asteroids coming our way. Still on a timescale of 10 to the 8, because a second consequence of what I just said about moving into a spiral arm in which we've got many more neighbors, one is one of those neighbors could produce a whole load of asteroids or comets, and that could be disastrous, but also one of those neighbors could go supernova. At the moment, we haven't got any massive stars close to us, and only massive stars can go supernova. Stars like our sun will not end their lives that way. You need to have a mass at least 10 times larger than our sun for a star to end its life as a supernova. But if we've got lots of neighbors, as we will have on this timescale, maybe one of those stars will be a supernova candidate. We know that a supernova, if it went off within 100 light years of us, that would be really bad news. Okay, this is only an artist's impression of a supernova cutting a planet in half. Ignore that, that's just a bit of whimsy. But we know that if a supernova were to go off at this sort of distance, remember Betelgeuse is 600 light years, that's a sort of safe distance. If a supernova went off 100 light years away, that would be a problem. If a supernova went off 20 light years away, the radiation from that supernova might end all life on Earth. And that sounds a bit dramatic, but bear in mind, we know supernova have gone off close to Earth in the past. There is evidence. When a supernova goes off, it leaves a telltale sign, an isotope of iron called iron 60. Any supernova within about 100 light years is close enough that it could produce iron 60, and some of that iron 60 could be deposited on Earth. And when we look in the Earth sediment, we find traces of iron 60. As far as we can tell, that can only come from supernova, because iron 60 has got a half-life of a few million years and will change into cobalt and then into nickel. So if that happens on a timescale of millions of years, that means if we find some iron 60 in Earth sediment, it can't have been lying around for billions of years. It can't have been there when the Earth formed. This could only have been deposited on this sort of timescale, because otherwise, if it was any older, it would have decayed away with a half-life of millions of years into something else. So the fact that we do see iron 60, and we have no other way of explaining its presence, indicates that we have had some of our neighbors go supernova on timescales of the last fraction of a billion years or so. So it's happened before, it could happen again. I said that the moon was slowing the Earth down. The moon is raising tides on the Earth, and as a result, the rotation of the Earth is slowing and the moon is getting pushed further away. This has been going on this timescale for the last 100 million years or so. The moon is continuing to rob some of the angular momentum of the Earth and push the moon into a higher orbit. At this point, 100 million years into the future, the Earth is now spinning not once in 24 hours, it's now spinning once in about 25 hours. No way leap seconds can keep up with that. We can't keep adding a leap second continuously to try and keep changing our clocks. This would be the point at which we would start decimalizing our clocks and talk about 100 lots of quarter hour or something in order to keep track of how the Earth is changing. But because the distance to the moon is increasing, because it's robbing the Earth of angular momentum, it won't be long before the distance from the Earth to the moon will be so large that it will be no longer possible to see a total eclipse of the sun. So at the moment, we have this lucky happenstance that the disk of the moon can just about cover the disk of the sun. There's a bit of variation because the moon's orbit is elliptical, so the size appears to change in the sky, but the size of the disk of the moon is just about enough to occasionally cover the sun if you're at the right place on Earth. If the moon continues to move away from Earth, its disk in the sky will simply be too small because of its distance to completely cover the disk of the sun. And so we won't be able to see a total eclipse after this particular point, about 1 billion years into the future. We can still have partial eclipses where some of the moon covers some of the sun, and it might still be possible for the two to be lined up so you get a ring of fire, the sun peeking around the outside of the disk of the moon, but no more total eclipses of the sun from this point onwards. A second consequence of the moon moving away, apart from the fact we'll never see a total eclipse again from the surface of the Earth, the moon has a rather important stabilizing effect on the spin of the Earth. The tilt of the Earth, otherwise known as the obliquity, is a value which is about 23.5 degrees, and its value, the tilt of the Earth relative to the orbit, hasn't changed by more than about a degree in all of the records that we can see. We can get an idea of the tilt of the Earth by looking at seasonal variations going back through historical records. But historically, we don't think it's changed by more than about 1 degree either side. If I just run that again, the actual little tilt you can see here, that's the variation I'm talking about. It's absolutely tiny on the grand scheme of things. And part of the reason for that is the moon has been holding it in that position. If you wanted to change the Earth's tilt by more than that, you would have to change the angular momentum of the moon, and that's not really possible when the moon is close to the Earth. But if the moon is further away from the Earth, it's been calculated that if the moon is, say, 25% further away from the Earth, it will no longer lock the Earth at a particular tilt, and the Earth's axis could then tilt erratically from vertical to horizontal and anything in between. And that would result in radical changes to the Earth's climate. So again, we're lucky that at the moment the moon is close enough to effectively give us stable seasons, but it won't always be that way. Still on a timescale of 10 to the 9 years into the future, 1 billion years into the future, Voyager, remember Pioneer has got a plaque which would be eroded after 10 to the 7 years or so. Voyager contains not a plaque as such, but a gold disc, a phonogram, containing sounds of Earth, greetings from Earth as well as music from Earth. This is thought to live on a timescale of about 10 to the 9 years. In other words, after 10 to the 9 years, well, the metal itself will start to evaporate and it will be difficult to actually use this as a phonograph. Why is it 10 to the 9 rather than 10 to the 7? If this is flying through the interstellar medium, how is it that this disk lasts longer than the plaque that's on Pioneer 10 and Pioneer 11? Well, this phonogram is protected by a cover, and the cover is going to get thoroughly pitted and eroded, but it will protect the disk underneath the phonograph. Now that's good, except that this is going to be unreadable on short time scales, and the cover contains the instructions for how to read the phonogram. So for us it's obvious, it's a disc, you put a stylus in, you play it like a long playing record, for those of us who remember long playing records, and the instructions of this, you need to spin it at this speed and put this stylus in, the stylus is provided. So unfortunately, the instructions are going to be lost on time scales less than 1 billion years or so. So again, Voyager is going to be passing through other solar systems on time scales of 10,000 to 100,000 years. So on a time scale of 1 billion years, Voyagers 1 and 2 will have passed through hundreds, thousands, possibly tens of thousands of solar systems. And again, it's possible that any alien intelligence could pick up Voyager. Perhaps if they're really intelligent, they can figure out how to play the record, even if they've lost the instructions on the cover there. Let's hope that's the case. Otherwise, these records of greetings from Earth might be lost forever. On a timescale of billions of years into the future, our sun is going to start to change. The sun's luminosity, it's not a red giant yet, but the sun's luminosity will start to change. It's been calculated that as it moves towards its red giant phase, once its hydrogen fuel starts to run out, its luminosity is going to increase by something like 10% every billion years. Doesn't sound like much, but over a few billion years, that means a large change in the sun's luminosity. That means the Earth is going to be driven to higher and higher temperatures. At some point, the surface of the Earth is going to reach a fairly balmy 80 Celsius, which means the oceans are going to effectively boil dry. We're going to have to find somewhere else to go for a little while. Even going underground is not going to help. It's going to be equally hot. So if we want to continue living on Earth, we're going to have to find somewhere else temporarily and then come back to the Earth once the sun has passed through its red giant phase. But isn't that going to be a problem? Because when the sun goes through its red giant phase, it's going to get very large, and it's been estimated that the surface of the sun could effectively reach the orbit of the Earth. And you say to yourself, well, surely that's going to be a problem, isn't it? Because if we think about the surface of the sun, if it's really close to the Earth, there's no way we could survive. It'll be completely incinerated. Well, maybe, because people are doing calculations to try and work out whether or not the Earth is going to be engulfed when the sun, because of the end of its life, once the hydrogen starts to run out, the outer part of the atmosphere is going to swell up, and if it is swelling up to the point where it's roughly the radius equal to the Earth's orbit radius, doesn't that mean the Earth will be engulfed? Well, no, because as the sun goes through its red giant phase, there's going to be very strong solar winds. A lot of matter is going to be coming off the surface of the sun. So the sun will be losing mass as it swells up. And if it's losing mass, that means with a smaller gravitational pull on the Earth's orbit is actually going to increase. And it's a balance between which one wins, the expansion of the sun or the expansion of the Earth's orbit. The cartoon on the left gives us an idea of what might happen. As the sun expands, the Earth is going to move further away from the sun because there's lower gravity pulling it. So yes, the sun will probably expand until it's the size of the original Earth orbit, but the Earth isn't there anymore. The Earth will now probably be orbiting the sun, possibly as far away as where Mars is now. So it'll still be pretty hot, but it might not get engulfed by the sun, so the Earth might survive. Let's assume it does for the time being, for the sake of argument. The sun will go through its red giant phase and will become a white dwarf. It'll cool off eventually. So the Earth will cool off. So maybe at some point we can return to the Earth. But then there's a second problem. After the sun has gone through its red giant phase, the Earth will lose its magnetic field. At the moment, the Earth has a magnetic field because it has an iron or a nickel iron core, molten iron, spinning, which is effectively a dynamo generating a magnetic field. But that's nothing to do with heat coming from the sun. It's entirely due to the fact that there is heat from radioactive decay of elements in the center of the Earth. They've been there for billions of years, but on this time scale of order 10 to the 10, many billions of years into the future, that radioactive decay of elements will no longer be strong enough to generate enough heat to keep the Earth's core molten. If you haven't got a molten core, you've no longer got a dynamo, the Earth will lose its magnetic field. And if Earth loses its magnetic field, that means it loses its protection from, for instance, cosmic rays, which are raining down on it all the time from outside the solar system. Radiation from the sun, perhaps not so important once the sun is a white dwarf, but certainly cosmic rays will be a problem. It's thought that maybe this is what happened to Mars some time ago. Mars is smaller, it would have cooled off faster, it would have lost its magnetic field a lot earlier than the Earth, and maybe because Mars lost its magnetic field, it lost its protection from radiation and had its atmosphere stripped away. So maybe that's why Mars is the way it is, simply because it's smaller than the Earth. So perhaps we can survive the sun going through a red giant phase. Perhaps we can survive the loss of a magnetic field if we're clever enough. But bad luck always comes in threes. There's another problem around the corner, and that is the Andromeda galaxy is going to come crashing into the Milky Way on the same sort of timescale. Quite a few billion years into the future, the Andromeda galaxy, which is a beautiful sight at the moment, either with naked eye or with binoculars or a small telescope, that is going to get larger and larger and larger in our skies. This is a prediction in 3.5 or so billion years into the future, the Andromeda Galaxy is going to be a spectacular sight. And over the next fraction of a billion years, it's going to basically pass through. The two galaxies are going to pass through each other. Very few stars are actually going to collide. It's very unlikely that our sun is going to be hit by another star in the Andromeda Galaxy. Even though there are 100 billion stars in one galaxy and 100 billion stars in the other galaxy, they will probably pass through each other with none of those stars hitting each other. But there is going to be a riot of new star formation as the two galaxies pass through and the gases that are in both galaxies end up getting mixed together. The Andromeda Galaxy will pass through the Milky Way, come out the other side, and then eventually they will settle down over a billion years or more, and there will be two centers. Perhaps you can see the bright patches here, top left and bottom right, because the supermassive black holes that are at the center of our galaxy and the center of the Andromeda Galaxy will end up orbiting each other and in a long time in the future end up merging together. So it is not cataclysmic. Having galaxies collide with each other is a perfectly normal part of galaxy evolution. It doesn't represent the end of a galaxy's life. If anything, it represents new star birth. And so you can get a whole load of new star formation whenever galaxies collide with each other. Finally, the dance between the Earth and the Moon comes to an end. On a timescale of order 100 billion years or so into the future, remember, the Earth has been slowing down. It used to be one day, and the Moon used to go around the Earth in a month. But now, after 10 to the 11 years, one day is the same thing as 1 month. In other words, the length of time it takes the Earth to spin once is the same as the length of time it takes the Moon to go around the Earth. The Earth and the Moon are now tidally locked together. At the moment, the Moon always has one face pointing towards the Earth. Eventually, we'll find the same is true of the Earth. One side of the Earth will now always face the Moon, just like the Moon has been doing for many billions of years. So that means from one point on the Earth, the Moon will never change in the sky. It'll still go through phases, but it will never move from a particular point in the sky. So half of the Earth will see the Moon, and it will never rise and never set. The other side of the Earth, they'll never see the Moon at all, because it will always be the same face of the Earth facing the Moon. And by the way, this looks like an artist's impression. It isn't. It's a genuine picture. It looks a bit odd because it's taken from a long way beyond the far side of the Moon, and so we're seeing basically the far side of the Moon, not the familiar near side of the Moon, which is what we normally see in our sky. So finally, we've got the red rectangle to the right-hand side. We're now 10 to the 12 years into the future. I said that the Milky Way and the Andromeda Galaxy are going to collide with each other. There's the Milky Way and some of its satellite galaxies around it. There's lots, dozens, possibly even hundreds of small galaxies around the Milky Way. And we've said that on timescales of order 10 to the 10 or so, 10 to the 11 years, we know that the Milky Way is going to collide with Andromeda. Eventually, when we think about Andromeda Galaxy M31 and other galaxies like M33, the Triangulum Galaxy, all of these galaxies are going to collide with each other and merge into one mega galaxy. It's not going to be a spiral. That's just a little icon in the middle to remind us that all of these are going to merge together. Essentially, all of the galaxies that we commonly call the local group, meaning all galaxies that are just a few million light years away from where we are, they're all going to merge together. But what's going to happen to galaxies much more remote? All of these are gravitationally bound to each other. But what about galaxies that are way out there, tens of millions, hundreds of millions, billions of light years away? What's going to happen to those galaxies? At the moment, it's a bit counterintuitive, but at the moment it's actually possible to image galaxies, even if those galaxies are receding from us because of the expansion of the universe at speeds greater than the speed of light. As a COVID challenge back in 2020, I set myself the task of imaging a quasar that's actually so remote, it's about 25 billion light years away, receding from us at twice the speed of light, but it's possible to photograph it with a camera even without using a telescope. That was what I did when I couldn't go down to the pub and see my friends during the COVID lockdown. And if we think about what's going on when we look at a Hubble deep field, most of the galaxies, or at least a large fraction of the galaxies that we see in a Hubble deep field, a lot of these galaxies are so remote they are receding from us faster than the speed of light because of the expansion of the galaxy. It's a little bit counterintuitive. How can the light ever reach us if these objects are moving away faster than light? But it is actually possible. But what is the point of this particular slide is to say that on a timescale of 10 to the 12 years or so, galaxies, because of the expansion of the universe, will be taken so far away from us, it will be beyond our horizon. It'll be impossible to image them. And if we think about a civilization that pops up at a 10 to the 12 years into the future, if they build themselves a Hubble Space Telescope and look out into the cosmos, what will they actually see? No matter how good their telescope is, they will see no galaxies whatsoever. They will only see some stars which are part of their own galaxy. This is nothing to do with technology. It is simply a fact that if the universe continues to expand the way it is doing at the moment, then on this timescale, the galaxies will be taken so far away, light will never be able to reach the telescope or the observer from these great distances. So it's sobering to realize that we are lucky in the sense that we can see 1 trillion galaxies in our observable universe. If we wait a while, we will not be able to see any of them. So we're lucky to exist at this particular point. If we had cropped up 10 to the 12 years from now, we would not be aware of the fact that the universe is full of galaxies. We would think that the entire universe is just our own Milky Way. I haven't been through the details, but all you need to know about how the universe began is that it took about 3 minutes to make all of the hydrogen in the universe. But we are talking about 1 trillion years into the future. It might only have taken 3 minutes to make all the hydrogen, and that happened 13.8 billion years ago. But after 1 trillion years, the hydrogen is running out. There's not an infinite amount of hydrogen in a given volume of the universe. There's only a finite amount. So if the hydrogen is running out, presumably there will be no new star formation. Again, a separate talk discusses how stars are actually made. Some people believe, hypothetically, although if there's no hydrogen, many people believe if there's no hydrogen you can't make stars because stars are made from hydrogen. Hypothetically, is it possible to make stars out of something heavier? Could you start with a heavier element rather than starting with the lightest element? Some theorists have said, hypothetically, might it be possible to make stars out of heavier materials, heavier elements, heavier gases? And some people have said, well, yeah, maybe you can actually make stars with nuclear reactions at the core, but heavier elements lead to lower surface temperatures. So instead of having a surface temperature of thousands of Kelvin, maybe you can make stars with surface temperatures of only hundreds of Kelvin. Is it actually possible to make a star with nuclear reactions at its core, but a surface temperature that's cold enough for ice to form? Frozen stars. And when I say frozen stars, well, it might be that you're thinking of, let's do that again. Frozen stars, Disney has its own version of what a frozen star looks like. That's a frozen star according to Disney. That's not what I'm talking about. So if that's the picture you've got in your head, let it go. Because thank you, what I'm talking about is nuclear reactions at the core, but ice in the atmosphere. Some people believe that's possible. Many scientists say, no, you absolutely need hydrogen to make stars. So if all the hydrogen is running out, there can be no new star formation. So in order to make any sense of what happens next, we have to just take a very small detour and say, well, do we understand what's happening to the universe before we think about what's happening to the stars? So we believe that if you look at a graph of the relative size of the universe as a function of time, so we've got billions of years along here, and we've got relative size, it doesn't matter what the units are, it's all just relative, The various coloured lines represent how the universe might have behaved and might behave in the future, and the different coloured lines correspond to how much stuff there is in the universe, how much matter, how much energy. So that's us now, relative size of 1, and that's us 13.8 billion years after what we believe is the start of the universe. The actual time the universe started depends on the evolution of the universe. It depends on which model we use for where we think we are in terms of evolution. Everybody agrees with what's going on now, but the past, and indeed the future, will depend on how much stuff is in the universe. If there's an awful lot of matter in the universe, then gravity will grab hold of that, and the expansion of the universe will eventually stop and come back, and we'll have a big crunch in the future when the universe expansion stops and reverses and comes back again. But we don't think there's enough matter in the universe to do that. We don't think we're on the orange curve. As best we can tell, that the universe is more like the red line. We think that's the best guess of the universe in which we live is the one that contains a certain amount of matter and energy and puts us on the red line. Notice that the red line not only doesn't turn back, it doesn't even seem to want to slow down. It seems to be accelerating. The universe expansion is getting faster and faster and faster. Now, we're not sure if that's right or not, but all indications are that that's what the universe is actually doing. So we don't have to worry about the universe having a crunch. As far as we can tell, the expansion will continue forever. And in order not to keep you until midnight, we need to change the numbers at the top of the screen here. We got to 10 to the 12, and each box was 10 times further into the future. But now we're going to have to change gear because each box is now 1,000,000 times further into the future. So we're talking about a zillion years or a gazillion, I don't know what adjectives we need to describe these particular time frames, but this is, of course, ridiculous times into the future now. So before we took this little aside to check on what cosmology is telling us about the expansion of the universe, we said that after trillions of years, all the hydrogen is running out. If we need hydrogen to make new stars, and stars do not live forever, massive stars only live for a short time, even very lightweight stars might only last for trillions or tens of trillions or hundreds of trillions of years. They don't last forever. So what are the consequences of all the hydrogen running out? There will come a time when there are no more stars shining. It'll not be for quite some time, but it is going to happen. The age of starlight will come to an end. The stars will still be there. They'll no longer be shining, but if you like, the dead husks of those stars will still be orbiting around their galaxies for a little while, like zombies. There will be white dwarfs, neutron stars, and black holes. It sounds a bit odd to talk about white dwarfs not shining, but they're only white because they're hot. They will cool off and they will go dark. With no nuclear reactions to keep them warm, even a white dwarf will end up as a black dwarf as it cools down. Stars will be ejected from the galaxy as they all interact with each other, and some stars will be eaten by the supermassive black holes. From here on, SMBH is supermassive black hole, which we think is at the core of essentially every galaxy. Now, we've mapped out magnetic fields in other galaxies. That's been done by, for instance, this infrared telescope in a 747, the Stratospheric Observatory for Infrared Astronomy. That's now decommissioned, so watch out for it on eBay if anybody wants a second-hand 747. So the matter, we think, follows these magnetic field lines into the supermassive black hole, which you can't see in this image, right in the center. So we think the magnetic fields help funnel all of the matter into the supermassive black hole at the end of a galaxy's life. What happens to all the atoms in the universe? Well, we're not too sure. We know that atoms have a positively charged nucleus and negatively charged electrons buzzing around them, and the positive charge in the nucleus is the result of having protons there. Now, we don't know if protons are stable or whether protons will ever fall apart. If they do fall apart, they're unlikely to do so on timescales much less than 10 to the 36 years into the future. But we can't be absolutely sure because, of course, we're extrapolating a long way from our current experiments. But it is possible that protons will decay, and that means every atom in the universe will fall to pieces. Even if they don't, atoms have only got a finite life. Because there are no atoms in neutron stars, there's only basically neutrons. There's no atoms in black holes, they're crushed out of existence. So if the only atoms in the universe are in white dwarfs, which then become black dwarfs, eventually even black dwarfs evaporate. It's a quantum mechanical effect that I'm not going to go into in detail, but it means that there will be no longer any atoms in the universe beyond this point into the future. There'll still be matter, but no atoms as such. Black holes will merge together. Remember I said that galaxies merge and eventually they're black holes like the Andromeda, and Milky Way black holes will eventually spiral around each other and merge together. We think that will happen across the universe. And black holes will grow from millions of solar masses to billions of solar masses, perhaps even trillions of solar masses. Black holes will exist on these ridiculous timescales, 10 to the 54 years into the future. But even black holes are not eternal. Even if that's all that's left in the universe, they do not last forever. They evaporate. According to Stephen Hawking and other eminent scientists, it is thought that there will be radiation from the surface, or at least the outer part, the just above the event horizon of a black hole. Yes, you have to wait a really long time to see that evaporation. We haven't measured it. It is, at the moment, conjecture, but many scientists believe this to be the correct explanation of what's going to happen to black holes. So very briefly, why do black holes evaporate at all? Well, according to quantum mechanics, it's possible to take some energy and to generate matter and antimatter, or a particle and an antiparticle. Borrow some energy, make some stuff, they annihilate, and they pay the bill back again. You borrow energy from effectively nothing, you make particles and antiparticles, then they annihilate and you pay the energy back again. What's that got to do with black holes? Well, if you think about a particle and antiparticle being generated just outside the event horizon of a black hole, what if you borrow some energy and then make a particle and an antiparticle, but whoops, one of them falls into the black hole and the other doesn't? It looks like something has come out of the black hole. It looks like it's radiating something. And that was proposed by Hawking. It's now being called Hawking radiation, as I say, not experimentally confirmed, but widely believed to be a process by which all black holes will eventually evaporate. The radiation increases as the size of the black hole decreases, so really large black holes evaporate very slowly, and as they get smaller and smaller and smaller, the radiation increases and increases until the black hole disappears in a flash of radiation. And even the largest black holes, even the ones that are trillions of solar masses, even they will evaporate eventually, though you'll have to wait trillions of times longer than waiting for a solar mass black hole to evaporate. Notice that we've now arrived at the right-hand end here, 10 to the power 84 years into the future. Is that the end of the universe? Well, it's the end of all matter. All you're left with is radiation. You're just left with some electromagnetic radiation floating around the universe. There is no matter left at all. We are talking about 10 to the power 100, a googol. Not that googol. That googol is a misspelling of the other googol. 10 to the power 100 is a googol. And after a googol years, it's been calculated that a black hole, every black hole in the universe will have evaporated. It's really difficult to get your head around that number, But that doesn't stop mathematicians twiddling the numbers and finding that 1 Google years is what you need for the most massive black hole to evaporate. And just to make the point of how stupid 10 to the power 100 actually is, there it is written out in full units after we make the observation that nothing interesting happens beyond this point. Let me just, there we go. 10,000 million. I'm not going to read it all out. But with no matter left, nothing interesting happens. The universe will continue to expand as far as we know. It will continue to expand, radiation will continue to fly across the universe, but there'll be no matter in the universe, and therefore there'll be nothing of consequence happening beyond this point. So that's as close, if you like, to the end of time as you can get. And Woody Allen had a good phrase for that. Eternity is a very long time, especially towards the end. And one of my favorite cartoons is XKCD, and they had a very interesting way of putting the human scale on top of these ridiculous numbers. They said a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. So the universe is going to be really boring in the future. So let me finish with a slightly more upbeat epilogue. We live in a golden age. The sun is middle-aged and stable and well-behaved. The moon is at just the right distance to stabilize the Earth's axis and hence to stabilize the Earth's seasons. As a bonus, it's also just at the right distance to give us the spectacle of a total eclipse of the sun every once in a while. And thanks to evolution, we are able to explore and discover and understand the universe in which we live. And we're able to do that by, for instance, building spacecraft and sending them out to visit our nearest neighbors in the solar system. And we are capable of building telescopes that can take images of billions of galaxies at distances of billions of light years. We could not have done this in the early universe because we needed generations of stars, generation upon generation upon generation of stars, to convert hydrogen into helium and carbon and nitrogen and oxygen and phosphorus and calcium and iron and all of the elements that make us us. And we've just seen that trillions of years from now, in the future, the universe will be dark and the universe will be boring. So the best time to exist? Well, it's now. Thank you all very much.